So a couple of you asked me questions about the third and fourth problems that we have. The first and second one was very simple and straightforward, coming directly from your lecture notes, right? The first one has to do with the pore water pressure in positive terms and in negative terms, right? So in saturated state and in unsaturated state. Remember, we had the concept of positive pore water pressure, which happens in saturated media, right? And it has a negative effect on the strength of the soil. Remember how you calculate the strength of the soil? Tau was C plus sigma prime times tangent of phi, right? So that pore water pressure, the positive pore water pressure, its net effect is going to reduce the sigma prime, right? So the sigma prime in the equation goes down, and therefore at the end of the day, the ultimate strength will go down. On the other side, we had the positive effect of strength that has to do with the negative pore water pressure, right? So the negative pore water pressure, remember we talked about the capillary rise, we talked about the surface tensional forces, right? So that has to do with the negative pore water pressure that happens in the above the groundwater table. So that was the case that you have to essentially talk about two things. Positive pore water pressure happens in saturated state, it has a negative effect on the strength. On the other side, negative pore water pressure has a positive effect on the low tier capacity. So that's basically what you needed to talk about in terms of the first question. The second question had to do with confinement, right? The confining pressure. The role of confining pressure when you're looking at the strength test. Remember, we had two types of strength tests. We had direct shear test and we had triaxial test, right? So we did a triaxial test. In the direct shear test, you place a surcharge, and that surcharge will result in the interaction of those solid grains with one another. That translates into the confinement, right? That basically means that you get higher strength properties. So how do you apply the confinement in the direct shear test? By the surcharge, by the weight that you place at the top of the soil. On the other hand, when you're looking at triaxial cell, that has to do with the all-around confinement in the cell, right? So we call that cell pressure, minor principal stress, sigma 3, and all that, right? And then you have to substantiate your claim with a plot. The plot was, remember we were looking at the stress-strain curves, the higher would be the confinement, the higher would be the stress at failure, which we called it the strength of the material. So that's all you needed to show in the second part. Now the third part was looking at the envelopes. So let's quickly take a look at that. So we had multiple envelopes that you needed to discuss the strength behavior of the material. You had tau here, you had sigma here, and then you had one, two, three, and so, what kind of behavior do you expect from soil number 1? This is the envelope for soil number 1.
It's sand, very low.
Right, so what is the intercept? 0. What's the implication of that? Cohesion-less material, right? So that would be a good example for that New Mexico white sand material that we talked about, right? So that was very simple and straightforward. The other thing that we talked about, if you recall, we talked about the location of the low Coulomb failure envelope. The higher it would be, the higher would be the strength of the material. So anything that is falling above, it has to do with higher strength, right? And the question was about two systems. One was airfield runways, the other one was a multi-story material building, basically, right? So those are essentially subjected to high magnitude of the stresses, right? Which one would you choose? The one that is higher, right? All right, so those are, majority of you got those parts right. Now the part that was a little bit challenging that some of you got right, some of you didn't, and that has to do with the stress sensitivity of the strength of the material, right? So that's also very simple and straightforward if you just look at these plots. What that means is that the higher would be the magnitude of the stresses applied, the higher would be a strength. These are all ascending curves, right? In very simple terms, you don't see a flat line. So what would be this kind of behavior? If my mole Coulomb failure envelope looks like this, it means that it's not as stress sensitive, right? So it means that you have different values of the stress, but you end up with the same tau sub f. or strength of the material. So that's basically what it means when you're looking at the stress sensitivity of the strength of the material. And you're also very familiar with that from the very first lecture. Remember we talked about if you apply the load, multiple load on a bucket of soil, what happens? Reduction of the void content, right? Better interaction. Therefore, the higher would be the magnitude of the stresses, the higher would be the strength of the material up to a certain point before you see the failure takes place, right? So that's basically what it means in terms of the stress sensitivity of the material. Now, the last question has to do with parametric analysis of geostatic stresses. And that was very, again, simple and straightforward. All you needed to do is basically plot the vertical stresses versus depth. How do you calculate that? Gamma 1 times H1, gamma 2 plus gamma times H2 plus gamma 1 H1, and all the way at the bottom of the layer would be gamma 1 H1 plus gamma 2 H2 plus gamma 3 H3. Now the point there was to use the proper unit weights, right? One case you had moist unit weight, the other case you had saturated unit weight. Moist unit weight means that it already embedded the component of moisture in it. It's not saturated because we know that in natural state your soil has some moisture in it. That's why we call it moist unit weight. And then the saturated state would be when it is fully saturated, right? And you needed to make sure that your saturated unit weight shows in the total stress calculations. Once you subtract saturated unit weight from gamma W, you end up with gamma prime, or the buoyant density. That basically comes up in the equations. The things that you have to show essentially there is the change in the slopes, right? Remember, from one medium to the other one, the slope of the lines are going to change because the slope of the distributions are unit weights, right? The unit weights in each layer is the slope of the line. So that's basically what you had in your exam there. And you notice you do not even need to use your equation sheets. Right? So that's what we had for the first exam. All right, so that's what we needed to talk about the first exam, and also we need to talk about another thing. So some of you noticed that at the end of the exam, I mentioned that you received a report that two of your classmates committed cheating in the second exam. So by law, by university law, I have to report that. And the way that it works in our department is that we have a departmental committee. I send a report there, we take a look at that, and it goes to the college, and college directly send that to the academic dishonesty committee that we have. Depending on the type of cheating and academic dishonesty that we have different kinds of punishments. You probably noticed that obviously there are different levels and different ramifications for it. If it's a copying from, say for example, a homework assignment, there's a different consequence as opposed to cheating in an exam, right? So the things that they look at is, say for example, if someone comes in and misreports the reason that he or she was absent in one class. That also goes to the academic dishonesty. Cheating in the homework assignments, that goes there. Cheating in the exams, that would be the highest one. And again, the consequences would be from losing one letter grade. Say for example, if you got a B, it goes back to C. If it's a C, it goes back to D. That's the lowest punishment there is, and there are also higher punishments. It has to do with probations and being dismissed for one semester. So I'm not going to talk about the ethical consequences or moral ramifications of that. You're very familiar with that. But let's talk about it in terms of numbers, right? See, because nobody will talk about what would be the cost for cheating. You think that you tilt your head and look at your friends right next to you, and you might be able to, I don't know, get 10 points, 20 points, right? And at the end, no one catches you, you think that you won. Now let me tell you what happens if you don't win. That has to do with the cost analysis. So you guys are going to be engineers in about a year or so, right? So let's talk about the financial cost associated with cheating, right? So for the exams, probation would be, or the consequences would be dismissing from the university for one semester. So that basically means that you graduate one semester early, right? So it would be 6 months of delay in graduation. So I did some calculations for you. So let's see what happens. Constant cheating. Alright. So as junior engineers, you can expect, if you stay in El Paso, you can expect somewhere around $55,000 per year. That would be what you can expect here in El Paso. If you decide to go outside of El Paso, you might end up getting a whole lot more. One of my students graduated last semester, he's getting about 68. So that's in Houston. Just want to let you know what the ranges are, right? So that's that. So let's talk about the settlement analysis of soil. By the way, the exam papers are ready. You can pick it up from the lab. Your TA is going to be in the lab today. And from 1:30 to 2:30, she's going to be there and you can pick up your exam papers. Alright, so let's talk about the settlement of the soil and see what we mean by calculation of the deformation beneath a foundation. Alright, so we have, so far we talked about the general stress strain curve, right? Remember, based on the direct shear test and also the triaxial test, you had the shear stress, you had the shear strain, and remember we had two distinct behaviors, right? So we had one case for the case of dense material. Which one was dense? Right, the one that has higher strength is the dense one. And we call this one tau sub F. Alright, so what do I have here? I have shear stresses versus shear strain of the material here. Where do I get the stresses? Based on the stress calculations that we talked about. Remember, we talked about the different types of loads that we have in geotechnical engineering or in general in civil engineering. We had the geostatic stresses, that has to do with the weight of the layers. And then what else do we have? External loads, that has to do with the weight of the structure or anything that is pressing the point, right? So you can do those calculations. We do have the seepage forces, that has to do with the movement of water within the medium. We do have other type of loading conditions that we have, such as earthquake load, wind load, rain and snow load, and anything that is associated with environmental conditions. We do have stresses that are induced by the changes in the temperature as well. Those are called the thermal stresses. So we do have all those different kinds of stresses. And remember, we talked about the concept of superposition of loads, right? Superposition of loads essentially means that you have load A, there's a consequence, and that would be the stress associated with load A, the stress associated with load B, the stress associated with load C, and then you sum them up, right? So the principle of superposition is valid when you're looking at elastic systems. When we start getting into pavement design courses, when we talk about the asphalt layer, which is a viscoelastic material, now in that case, the principle of superposition is no longer valid. But at this point, superposition is valid, meaning that you can basically sum up the magnitude of the stresses and figure out what the total magnitude of the stress that is acting on the material is. If you're doing the LRFD design from your concrete, from your steel, you know that you have multiplying factors, right? So you also have to keep in mind that you inflate the loading conditions to ultimately get the stresses. That would be a whole different story. Yeah. But we know how to calculate the stresses, right? Now, the second part was getting the strength of the material. The strength of the material is that peak that we have here, that tau sub F. Calculation or determination of the strength of the material. How did we determine that? Remember, we go to the lab, we run the direct shear test, we run the triaxial shear test, and get that tau sub F, right? So up until this point, we know how to do the calculate the stresses. We know how to determine the strength of the material in our stress strain curve. What is left? The x-axis that we have. What is the x-axis? The strain, right? The deformation, right? So that would be the part that we have that has to do with the deformation calculations or settlement calculations, right? So that's basically the objective that we have from this point on. These 3 lectures is going to be primarily on calculation of the settlement of soils. deformation beneath the loading system that we have. Right? So that's where we are with respect to settlement calculations. All right, so in this lecture we have to talk a lot about different definitions that we have. And from next lecture we talk about how you can do the calculations. So there's a lot of theories here involved. And my suggestion to you is that for next lecture, make sure that you're comfortable with all of these definitions that we talk about today. Because afterwards we're going to talk about how you can go about doing calculations, and if you don't study this, you won't understand what's going on in the class. So you do have a reading assignment, not a problem-solving assignment. All right, so let's talk about the settlement analysis.
Understand, is this
Yes.
section 11 on
Yes.
the website?
Yes.
I can't. So refresh.
I'll post it this afternoon. All right, so for the settlement analysis, if you want to plot the settlement versus time, we essentially have two behavior here. Alright, so you can subdivide the settlement into two main categories. One is called the immediate settlement. The other one is called time-dependent settlement, as it's shown in this plot. Right. Alright, the total settlement can be subdivided into two main categories. First one would be SI, which is immediate settlement. And S sub T is called time-dependent settlement. As you can see, in the first segment, there is no time dependency. It happens immediately. As soon as you apply the load, you see some deformation immediately will develop underneath the loading condition that we have. But the second part has to do with time. As the time passes by, the deformation increases with time. And that's the part that is going to be a little challenging to be able to get that. So let's talk about the first one quickly and see what that means, and then we get into the time dependency of the settlement and get into the consolidation. Alright, so let's talk about the immediate settlement. Alright, so what does immediate mean? It's quick, right? So what does that mean? It's fast. Happens at constant water content, meaning that the moisture state of the material doesn't change. As soon as you apply, you essentially will see some deformation is taking place in the system. So it happens at constant water content, and that's going to be the predominant factor that we have. Theory of elasticity is valid. What does that mean? Theory of elasticity. Remember we had in one of the lectures that we talked about, remember for the calculation of the external loads, the first few lectures, or the first few slides were about the theory of elasticity, right? So remember, elastic material is, right, So if you have a deformable body, you apply the load, the deformations will bounce back immediately after you remove the loads, right? So that means that there is no permanent deformation deposited in the material. That's what it means in terms of an elastic material. Now, if you want to characterize that material, you need two parameters, or two material properties. Those are Poisson ratio and elastic modulus, right? So you need two material properties, elastic modulus and Poisson ratio, to be able to calculate the deformation associated with the elastic deformations, right? So that's basically what we have in terms of the calculations. So let's quickly talk about how you can do the calculations here. It's very simple and straightforward. We'll talk about that hopefully in our next lecture, but you can essentially calculate that as a function of distributed pressure at the surface, the width of the foundation that you have, or the loaded area, and you have a parameter here, and we'll talk about what that parameter is. Elastic modulus and Poisson ratio, right? This is the distributed pressure that acts on the material. B would be the width of the loaded area. I sub S, it's called shape and rigidity factor. Shape and rigidity factor, table 10.4 in your textbook. E is elastic modulus. Mu is Poisson ratio. So Poisson ratio, elastic modulus, distributed pressure, width of the loaded area, and shape and rigidity factor, table 10.4. So it's very simple and straightforward. You can do the calculation of S sub I, or immediate settlement, that we have without any problems. Now, the issue that we have is determining the time-dependent component of settlement. Let's talk about that and see what are the components of the time-dependent settlement, and then get into our lecture notes and see if we can conceptually take a look at it. Alright, so your time-dependent settlement can be decomposed into two components. So the time-dependent component can be subdivided into primary consolidation and secondary compression. So those are the two components that we have for the settlement calculation associated with the discharge of water and shifting of the particles, essentially. All right, primary consolidation by definition has to do with the discharge of the water from the medium. So let's think about that and see what that means in terms of conceptual definitions, and then move forward with the calculations in the next lecture. All right, so let's assume I have a clay layer, right? This clay layer is fully saturated, right? A fully saturated clay layer. What are the parameters or properties you expect from a clay layer? You can talk about the cohesional properties. You can talk about the particle sizes. They're small. The small particles create small tubes, right? Those nanotubes represent or correlated to permeability of the soil, right? So the permeability of the clay materials are high or low? Low, right? So this is the way that you have to think about it. Remember, permeability has to do with the speed of the water molecule that passes through the medium, right? So these nanotubes, the path of the traveling water molecule is going to be long. Therefore, it takes much longer for that water molecule to travel from the top of the layer to the bottom of the layer. Therefore, the permeability of the soil is going to be low in that case. Make sense? All right. So let's assume I apply the load at the top of the medium. What happens? So remember what we talked about in terms of the stress transference plots, right? You had it in your lecture notes. As soon as I apply the load, because of the fact that water is incompressible, also solid grains are incompressible, what happens? All the stresses initially will be transferred to the water within the medium. And as the water moves away, or discharges, or dissipates, what happens? The water pressure goes down. Do you agree? Yes. What else happens? Now you have the transference of pore water pressure to the effective stresses, right? So that was what we talked about in terms of the transference of the stresses. So this is exactly the mechanism here. You apply the load from the top, and then you see the water essentially travels outside of the medium. What happens? You see settlement will take place. How fast the settlement takes place depends on the permeability of your soil, right? That makes sense? That's basically what it means, the correlation between the permeability and time-dependent components of the settlement that we have here. So we have two segments here. We have primary consolidation. By definition, primary consolidation is settlement or change in the volume of the material associated with the discharge of the water from the medium. So when the water leaves the system, you see the settlement will take place. So that's the definition of primary consolidation. By definition, primary consolidation is gradual settlement of the soil medium associated with discharge of water. So that's primary consolidation. Now we do have the second component that is called secondary compression. The secondary compression, still researchers debate what the purpose of that is. A lot of researchers will say that it has to do with the shifting and readjustment of the particles at constant stress, which is similar to the creep behavior of the concrete that you're familiar with. Right? So this has to do with shifting and readjustment of the particle as constant stresses. Let's go back and take a look at what we talked about so far. Remember we talked about the immediate settlement. Immediate settlement happens at constant water content, right? And that's the predominant mode of deformation in unsaturated soils. That's also something to note. The second one, or the second category, has to do with the time-dependent component of settlement. So you have the time dependency. You can just basically subcategorize it into two main categories. Category one would be primary consolidation, and the second one would be secondary compression. Now tell me, primary consolidation, does it happen at constant water content or variable water content? It would be a variable water content. So that's another distinction that we have with immediate settlement and primary consolidation that we have. Now the last component also happens at constant. So water content, change in the moisture state of the material is not a play for this one. Change in the water content is the predominant factor that we have for primary consolidation. Alright, so we're talking about a settlement, and we're talking about the general definition of settlement that you're familiar with, and that has to do with the compressibility of the material and compression in general. So tell me, where else did we see compression or reduction of the volume? In compaction, right? So remember in the compaction, we talked about the application of the mechanical energy and seeing what happens to the volume of the material. The volume of the material will go down, therefore you can pack more material in the same mold, the Proctor test that you did, right? And at the end of the day, you can increase the magnitude of the mass per volume, and that was density. That has to do with the densification of the material and ultimately the increase in the mechanical behavior that is associated with the interaction of those particles. So we have compression or compaction, and then we have settlement. Those are essentially different components that we have. Alright, so here's the definitions: compression and compressibility. When a compressive load is applied to the soil mass, a decrease in its volume will take place, and the decrease in volume of the soil mass under a stress is known as compression, which is very similar to what we did in the compaction definitions. The The property of the soil mass pertaining to its tendency to decrease in volume under pressure is known as compressibility. In the graduate level, you see that with defined parameter is called coefficient of compressibility of the material, and that has to do with the volume reduction associated with incremental increase in the magnitude of the stresses. So that basically refers to that. In a saturated soil mass having its void filled with compressible water, increase in the volume or compression can take place when the water is expelled out of the voids. Such a compression resulting from a long-term static load and the consequent escape of pore water is termed as consolidation. So the definitions make sense, right? So we can move forward with the discussion that we had with respect to the transference of the stresses. Notice that if I have a soil medium, let's assume it's fully saturated and is subjected to this distributed load Q that we have here. The total stress is constant with time. That Q is essentially not changing with time. But what changes there is pore water pressure and the effective stresses. Remember, the effective stress, we call that the design stress as well. That's the stress that shows up in the equations. That's the stress that you have to use in your tau equals to C plus sigma prime times tangent of phi. So that's where it's coming from. That already has the influence of moisture in it, right? Because you already subtracted from U from it. Alright, so this is essentially the stress transference section. Immediately after you apply the load, you see the uptake of pore water pressure. We call that delta U as excess pore water pressure. Familiarize yourself with these terminologies, we're going to talk about that later. So we have excess pore water pressure, and that is associated with the loading that we have at the top of the lid. Why do we call it excess? Because we know that already you have some U in the system, right? Because it's moist. So you do have some pore water pressure within the U. And as the time passes by, as the water drains from the system, now you see the increase in the effective stresses. Therefore, you get better interaction between the particles and improvement in the strength properties of the material. All right, so that was what we had in terms of the stress transference. But let's take a look at the concept of consolidation and settlement of the material based on the piston, spring, and valve analogy that we have. We talked about this in a different way before, but let's quickly take a look at the general concept here. Let's assume that I had a leak-proof, waterproof system. This is a piston here. I can measure the pore water pressure. This piston is already filled with water there, and then you have this spring here. This spring represents the soil split, the soil particles that we have. Water inside this piston represents the water in the soil, right? And then you have a valve here. The valve opening is related to the permeability of your soil. If the valve is fully open, that would be a drainable system, such as question number 4 in your exam. Remember, you had SP there when you were looking at the location of the groundwater table. What was the significance of that? So you have SP on that level, and you had the same level of groundwater table. What's the significance of SP? Poorly graded sand, big gaps. What can you tell me in terms of the height of the capillary rise? 0, none, right? It won't go up. So you don't have capillary saturation in that. So that's what it means. So your pore water pressure should stop right there. 0 would be there. All right, so similar concept here. We have clay materials that they have low permeability. Now the way that we replicate it here would be the valve that is relatively shut, right? So just a little bit of opening. On the other side, we have the other component that has to do with the valve that is fully open, and that would be for the case of that SP that we talked about, the drainable layers. So what happens if I quickly apply the load? When I apply the load, all the stresses, let's assume that you just have just a little bit of opening, right, of the valve that replicates the clay layer. I apply the load, all the stresses will be transferred to the water here, right? What do I have here? Increasing the pore water pressure. Over here, and then you have higher magnitude of pore water pressure in this gauge here, right? And then, as the time passes by, what happens? the water essentially drains from the system, and that spring will be jammed. More water leaves the system, and that basically means that you have higher magnitude of effective stresses. Right? So this is called the piston and spring analogy that Terzaghi developed to basically show you what would be the mechanism of settlement in soils. So notice that this S that we have here is settlement, right? This is basically the deformation. This deformation has to do with the discharge of the water from the system. Another way that you can rationalize it for yourself is based on the void ratio. What was the definition of void ratio? How do you calculate void ratio? You had V sub V, volume of voids, over volume of solids, right? So that was how you calculate the E value or void ratio. All right, so V sub V over V sub S. How can you decompose a V sub V? Volume of voids. You have volume of air and volume of water here. Let's assume that it is fully saturated. So what happens with the discharge of water? Volume of voids goes down. Void ratio will go down, right? Because the solids are constant. Air, there is no air, and it's just the water, right? So the water essentially discharges, the volume of water goes down, and at the end of the day, you end up with lower void ratio. And for this reason, from this point on, when we want to describe the settlement of soil associated with the discharge of water, we plot void ratio versus magnitude of the stresses, or effective stresses. So from this point on, everything has to do with the change in the void ratio. And the change in the void ratio has to do with the change in the volume of water that is discharged from the system. And we know that you apply the load, you see the water essentially escapes from the system. And reduction of the void ratio with increase in the magnitude of the stresses. Alright, so these are the descriptions that we have with respect to what we talked about. So now let's quickly talk about the general definitions of the settlement of soil that we talked about, and then move forward with the rest of the definitions and talking about the components that we have. So you can subdivide your general settlement into immediate settlement and time-dependent settlement. Your time-dependent settlement has two other components. Consolidation, we call that primary consolidation, and the third term in that equation would be the secondary compression, right? The first component has to do with discharge. Does it have to do with the discharge of water?
No.
No, it happens at constant water content, right? The first part happens at constant water content. Consolidation would be change in the moisture state of the material. Essentially, it has to do with the dissipation of the pore water pressure from the medium. And the last one has to do with the shifting and readjustment of the particles within the medium, and ultimately that results in the settlement of the soil. So you have three components. Two of them are moisture dependent, moisture independent, and one of them is moisture dependent. So let's quickly take a look at the definitions together. Consolidation is the time-dependent settlement of soil resulting from the discharge of water from the soil pores. We have the primary consolidation, which is the change in the volume of the fine-grained materials by the expulsion of the water from the voids and the transfer of the stresses from the excess pore water pressure to the soil particles. We have secondary compression, is the change in the volume of the fine-grained soils caused by the adjustment of the soil fabric, the internal structure that we have after the primary consolidation has completed. So essentially what we have here is these three components. The first component is based on the theory of elasticity. You can quickly use one equation to be able to get that. Now the second and third one is a little bit challenging. For that you have to run the consolidation test. Alright, so let's quickly talk about what consolidation test is about and what we can get from it, and ultimately get into the equations in our next lecture. So we have consolidation test. You essentially have a top of water, and you place the soil inside a metallic ring and place the material inside the top of water. So that part is simple and straightforward. Now, you're going to place a surcharge at the top of the soil and let it sit for 24 hours. Why? because we are interested in the time dependency of this element here, right? So you want to make sure that the soil becomes fully saturated, and then you want to make sure that the material reaches an equilibrium. What is that equilibrium? The pressure from the surcharge and the uptick in the pore water pressure, right? And then the water essentially drains out. That would be your first step. So you monitor the deformation associated with the surcharge as a function of time. Next step, day 2, after 24 hours, double the magnitude of load. If you started with 100 kPa of the pressure, now the second stage would be 200 kPa. And again, let that surcharge to sit there for 24 hours and see what would be the settlement of the soil. Repeat that for 400 kPa. So you do that for 7 points in 7 days, and then you incrementally remove the loads. What happens if you remove the load? Yes. So for those of you who missed Jacob's hand gesture there, he basically said that your material will expand, right? You remove the load, now the water gets into the soil as collected there. So you see the swelling will take place. So you have the compression, and then you have the swelling that they're going to be counterbalanced. So let's quickly talk about that and talk about the distinction between the two. All right, consolidation versus swelling. The process involving a graduate compression happening simultaneously with the flow of water out of the soil mass and with gradual transference of applied pressure from the pore water to the mirrorless collector is termed as consolidation. Now the process opposite of consolidation is called swelling, which is the volume expansion due to the increase in the water content of the soil. Now why does consolidation happen in the field? It could be associated with the external static stresses, that could be the overburden pressure, or the static stresses associated with the weight of this structure. Weight of the recently placed fields on the soil, that would be the embankment, for instance, a highway embankment. Lowering of the groundwater table, we talked about the drawdown effect. Remember the changes in the unit weight of the material at the back end of the dams. And ultimately desiccation or the drop. In very simple terms, any time that you see the change in the equilibrium in the system, if you mess up the equilibrium, you see the changes in the deformations. So these are all going to be transferred into the material. Alright, so let's stop here. When we come back, we'll talk about the